Thank you very much for the kind introduction. I'm really grateful to the Physiological Society to present some data here today. We've seen quite a bit of reference to cardiac output and VO2 max across this meeting, and I'm hoping that in the next 10 minutes I can show you that we can perform some other heart measurements that can really tell us more about the physiology of different types of athletes. So we know that an endurance athlete will have a greater heart. They will have a greater volume within the heart because of the plasma volume expansion. They will also have a greater wall thickness, but these hearts are physiologically remodeled, so the relative wall thickness of the muscle to the inside volume remains pretty much constant and the same. We also know from seminal papers now for 20 years ago that these endurance athletes have a greater compliance. So in the diastolic phase, if you fill these hearts more with saline, or if you suck the blood out of the heart with low body negative pressure, there's a much, much greater compliance in these hearts. However, in a really elegant study a few years ago now, Ilkka Heinonen from Finland showed that the hearts of endurance-trained athletes seem to be over-perfused with blood at rest, and this is normalized to the actual muscle size, but under-perfused during adenosine-induced hyperemia. So we have a bit of a conundrum here and an open question, and we don't know what the mechanism for this is. So I turned to a really famous scientist of the 21st century to try and design this study. Unfortunately, Dr. Sheldon Cooper's exercise ability was not really up to scratch to this audience here. Nonetheless, unsurprisingly, Dr. Sheldon Cooper had some advice. Dr. Stohr, you know you should be looking at heart muscle twist and untwisting, so we proceeded to do exactly that. Now, it's absolutely known and clear now that due to the muscle fiber arrangement of the heart, which is in double helix, we get this twisting during heart muscle contraction. And if you ask an architect, this is absolutely key to any structures to equalize stress within any structure within a building, but also within the heart muscle. There's even been some indications whether the double helical arrangement of the DNA might also give it a bit more stability. The reason for looking at twist is demonstrated here with what I just said. Papers have shown that it is a stress distribution across the heart muscle that is implicated there, and the endocardium, the most inner layer of the heart muscle, and the epicardium are in a certain type of balance, and if these get out of balance, we might get an increased twist and also potentially underperfusion of the endocardium. We have previously shown that in a relatively normally distributed sample, some of our more aerobically trained athletes had a lower twist, and at the time we concluded that this was simply due to a greater efficiency. They needed to twist less, and we were really, really grateful and pleased to also be kindly invited to get on the cover of the Journal of Physiology. I now tell my students that that's the scientist's equivalent to a supermodel getting on the cover of Vogue. So I'll leave it at that for now. But in a follow-up study recently, which was entirely conducted by our collaborators in Boston, this is a 3-year longitudinal study showing that if you look at torsion, which is the heart muscle twist normalized to the size, because this increases over 3 years of training, it actually comes back down to normal levels, whereas this untwisting, which is really important, the recoil of the heart muscle still remains elevated, and independent studies by a Norwegian group have shown that this untwisting is really essential and reflects the restoring forces of the heart muscle. So we aimed, in order to understand the functional adaptation of the athlete's heart, and I'll remind you of the conundrum of overperfusion of the heart at rest, but reduced perfusion of the heart with adenosine infusion, and this is during the diastolic period when the heart gets perfused with blood itself. We aim to look at the effect of exercise training status on twist and untwisting rate during exercise. This is our study protocol. We had a wash-in period. This is in normoxia. 10 minutes of rest approximately, a 3-minute warm-up at 40 watts, and then 30%, 40%, and 50% of exercise capacity. These were 5 minutes long, and we collected data during the last 3 minutes of each stage. We added an additional condition, which was in hypoxia, 12% hypoxia. And there were two reasons for that. The first reason was we know that hypoxia is a really pronounced stimulus to increase myocardial perfusion. And we were interested in this during exercise. And then also we know that endurance athletes actually desaturate to a greater extent during exercise. So we were trying to tease out differences between untrained and endurance-trained individuals, and I want to highlight already that we had a 50% condition here in normoxia that I will come back to towards the end of my talk. These were counterbalanced, and finally, the last piece of our jigsaw was to look at sprinters. We've already heard talks this week about the differences in terms of sprint interval training, sit or HIIT, and endurance training. And one thing that has not been mentioned as much is the incredible functional buffering capacity, anaerobic capacity, so not the VO2 max, but the anaerobic capacity of these athletes. And to see how they deal with hypoxia and whether this has any influence on their hearts as well, we included a third group. We performed a sample size estimation with a power of 0.8 and an alpha level of 0.05 to get a significant interaction effect between the three groups in untwisting rate, and this came out as an N of 13. And so far, this is an ongoing project. I can tell you that the untrained we've completed. We have collected data on 8 endurance trained athletes and 6 400-meter sprinters. So I hope you forgive me that I don't present you with any statistical comparisons because this is not complete yet. But I think some of the differences I will show you are fairly obvious already. We used 2D and triplane ultrasound to look at LV mass, volumes, cardiac output. We use speckle tracking technology to look at the twist and the untwisting rate, and then some standard spirometry, hematology. And just to point out the exercise mode for these studies so that we can measure the heart during exercises on a supine tilted ergometer. So not exactly the type of exercise that you would do your training for and compete in. But it's the best way for us to actually get good quality data. So some results to confirm that we were in line with the literature, fortunately and happily. Our endurance athletes had a greater LV mass, the sprinters did not, and that remained the same when we normalized for body size, even though there weren't any major body size differences between these groups, but we still normalized the data. And similarly, that's the heart muscle. For the volume contained within the heart, the end diastolic volume, we see a similar difference. Endurance athletes have a larger end diastolic volume. The sprinters were somewhat in between, and I can tell you now that very rarely have sprinters been split in studies. So this is one of the rare studies we think that has actually included sprinters in this kind of work. In a seminal paper from 1991 in New England Journal of Medicine, grouped marathon runners and 200-meter sprinters, their heart adaptation into one group. So we're trying to split these now. So some functional physiological responses. We have the drop in saturation, of course, in hypoxia, and more in the endurance-trained. VO2 goes up with exercise, but as you would expect, greater in the trained groups at the relative exercise intensity than in the untrained groups. Interestingly, the sprinters drop a little bit in hypoxia, and there's some lactate data here. The cardiac output response was fairly similar. We would have potentially expected to be for the endurance guys to be a little bit higher, but overall fairly similar. So these are the main results now on torsion, this normalized twist for the heart size, and there are no major differences here, except for we can see that the untrained probably have the greatest torsion. And these data are important for the next slide, really, the main results, which is our untwisting rate, this diastolic recoil. And I would like to point out that already at rest in normoxia, both training groups are increased compared with the untrained group. If I show you this slide without the untrained group, the pattern becomes relatively clear. The diastolic relaxation properties of the endurance-trained heart actually goes down a little bit with exercise whilst it increases in the sprinters in normoxia. In hypoxia, we see a similar pattern, but then all of a sudden at 50% of the maximum capacity here, the groups start to come back together again. We're not entirely sure why this is, but this certainly would require further investigation. I've got 2 more slides on the results, and this one is really one to try and explain the previous results, the differences in the untwisting. It has been suggested that maybe differences in heart muscle function are due to the endocardium being perfused less. Therefore, you would expect the twist to increase, and this twist to shortening ratio indicates that how much twist do you have per heart muscle shortening, and if this increases, we probably have a slightly lower contribution from the endocardial fibers. And this is exactly what we would expect in hypoxia, and we see this in both groups. The only difference really is there where I showed you before, where the untwisting rate in the sprinters starts to come back down again. So there might be a greater underperfusion of the endurance athletes' hearts here compared with the sprinters. Just to, on the last slide, I want to show you some data on the re-oxygenation phase, because we think of hypoxia being a problem, but when you re-oxygenate, you might accumulate free radicals, you have a surge in VO2, and to quickly talk you through the slide, we have a control condition here in the black squares where we had 50% in normoxia, 50% in normoxia. The white circles, this is the untwisting rate again, is the diastolic function, 50% in hypoxia, and then immediately in normoxia again. So this is the untrained response. Endurance athletes don't seem to respond to this. Within the 15 to 30 seconds when we took the measurements, this says 1 minute, but the twist measurements were actually taken within the first 15 and 30, where the VO2 peaks remarkably. But the 400-meter sprinters are again more similar in that response in the diastolic relaxation properties compared with the untrained individuals. So to summarize and conclude, I think we must study the heart during exercise beyond cardiac output. There are some other markers. 400-meter sprinters appear to have a greater cardiac relaxation properties than endurance athletes, at least during submaximal exercise, and that's in normoxia and hypoxia. This torsion to shortening ratio increased during hypoxia, suggesting a reduced contribution and maybe even a perfusion of the endocardial fibers compared with the endurance-trained athletes. Following hypoxia, 400-meter sprinters augment their untwisting rate, but endurance athletes do not. And we think that we need to look at further stress markers of the heart and maybe tighten as well in future investigations. So I would like to thank my collaborators in particular, or my colleagues in particular, Jake Samuel, who's in the audience, without whom this study could not have happened, and some funding from the European Union. Thank you.